So we started out by saying the work energy theorem was said that the work is equal to the change in the kinetic energy. And then we started looking at the work and we were saying, well, some forces are conservative. And so we can break work up into work that's done by conservative forces. This is like gravity and springs. And plus the work done by non-conservative forces. And so this is like friction, or a person, things that aren't springy, right? And so then you can say, well, the work done by conservative forces plus the work done by non-conservative forces is equal to the change in the kinetic energy. But we also said that the work done by the conservative forces is equal to minus the change in the potential energy. That's kind of how we define the potential energy. We said it's the change in potential energy is minus the work done by a conservative force. So you can rewrite it this way, and then you can say minus the change in potential energy plus the work done by non-conservative forces is equal to the change in kinetic energy, or the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And this is where we said, if this guy is 0, then the total change in mechanical energy is conserved. If there's no friction, if there are no other forces like people pushing or a rope or something like that, then, and all those works are 0, then this stuff has to be conserved. That is to say, the change in kinetic plus the change in potential has to be equal to 0. So, if it is, then if the potential energy decreases, the kinetic energy has to increase, or if the kinetic energy increases, the potential energy has to decrease, and so on. And so now we can ask the question, well, what if there is a non-conservative force acting, right? And so just let me do an example of that here. So let's just do a little summary for work. When we started the chapter, we said, look, work is force times distance times the cosine of theta. It's kind of the component of the force in the direction of the motion times how far it went. And so F is the force, D is the distance, and theta is the angle between the force and the distance. We can find that the total work done, or the net work done, is just the net force times cosine theta times the distance. Often this is the thing we want. We want the total amount of work done. If you have if you're dragging something along the ground, here I'm dragging something along the ground, right, with a force this way. There might be a friction force going this way while I'm dragging it. There could be a normal force going this way, and maybe it's canceled with the gravitational force if it's horizontal and all that, it's on a horizontal surface and all that stuff. We can figure out what the net force is. These two guys usually cancel if it's on a horizontal surface, and these two guys would, you would end up with a slight net in this direction. So you would figure out what the net force is, and then multiply it by the distance. Maybe we moved it, to there, and then in this case, if the net force is horizontal and the distance is horizontal, the theta would be 0. But this tells the total amount of work done by all the forces. This might just be the force done by, say, this force, or you could do the work done by this force, right? So theta in each case would be the angle between the particular force you were talking about and the distance. So, for example, if we're moving horizontally, a distance d, and my force is perpendicular to that, then the cosine the angle between those two is cosine of 90 degrees, which is 0. So either one of these forces would produce a 0 contribution to work. All right, and so we talked about that. And then in the process of this, of getting this guy, we said, look, the net work done, and we derived this, is equal to the change in kinetic energy, right? And this is sort of the works from all the forces. And so, this was, where kinetic energy is 1/2 mv squared, and so you have 1/2 mv final squared minus 1/2 mv initial squared. But this guy is the work due to all the forces. And so then after we looked at this for a while, we said, well, you know what? Some of those forces, like gravity and springs, are conservative forces. And so we could break this up into work by conservative forces like gravity and springs, and then other things like friction or the pull force, that I just showed you a second ago, and maybe the normal force. And so we could split this up this way and write it like this. And then when we realize that these conservative forces like springs and gravity, those guys allow you to get the work back out of them. And so those things we called the work by conservative forces is minus the change in potential energy. And so what we would do is we'd do it this way. We'd say work by non-conservative forces minus the work done, minus the change in potential energy equals the change in kinetic energy. And then we just move this over to the energy side and we'd say work done by non-conservative forces equals the change in potential energy plus the change in kinetic energy. Right. And these are all the other forces that are acting, friction or me pulling and stuff like that. The potential energy is just the springs and the gravity. Maybe you have one of those in your problem, maybe you have both of them in your problem, maybe you have none of them in your problem. And then this is the kinetic energy. And so when you have no external forces acting, this becomes, we call this a statement of conservation of energy in an isolated system. By isolated, we mean there are no external forces doing work on the system. The system just does whatever it does. Gravity acts or the spring acts. So when the spring acts, pushing on the object, it gains kinetic energy and potential energy is lost because the spring is losing it by relaxing. And so conservation of energy in an isolated system. This would be called, if we were doing a thermodynamics class, the first law of thermodynamics. And so there's sort of a short summary of work and how it relates to energy. You might have heard when you were in middle school, energy is the ability to do work. So in this problem, the baseball player slides to a stop on the ground. How far does she slide if her initial speed was 6 meters per second? Her mass is 65 kilograms, and the friction force is 450 newtons. All right, and so let's draw a picture of her here. There's her baseball cap. Her arms are like this, right? Should have drawn a bigger head. All right, let me try one more time. So. Right, there's her sliding, here's the ground, right, and her V naught is 6 meters per second. There's a friction force going this way, F. We don't worry about, in this problem, we don't have to worry about the coefficients because they're just telling us the force is 450 newtons, right? And so she's going this way, and there's a force this way. So remember, this is our work energy theorem. We can have the work by conservative forces. Well, we can just say the work done is equal to the change in kinetic energy. In this problem, there's no spring and there's no gravity really. She's just sliding horizontally. And so, that's the only thing I have on the right-hand side. If there was a potential energy, I could just put it over here. Sorry. I could just put it over here. And then this would just not have the potential energies in it. This would be, like we were saying before, non-conservative forces. But there's no potential energy in this problem, and the only thing it's doing work on her is the gravitational force. I mean the friction force. And so I can say work by friction or work, is equal to work by friction, which is equal to the force of friction times the cosine of the angle times the distance, right? And so we know that she's sliding this way, right? Let me do that a little better. She's sliding this way somehow. I'm not going to draw her again, but this is where her head ends up. All right, I'll try to draw a little bit. This is where, there's her baseball cap, there's her legs, and so on. That's how she slides. So she's going this way, and the friction force is going that way. And so theta is 180 degrees. And so the work by friction is minus the force of friction times the distance, because cosine of 180 degrees is -1, and that's equal to the change in kinetic energy. They're asking us what the distance is, and so the distance is equal to minus the change in kinetic energy over the force of friction, or minus KE final minus KE initial over the force of friction. But the final kinetic energy is 0 because she came to a stop, V equals 0. The initial kinetic energy, so it's minus and negative, so it's a positive. This becomes 1/2 m V naught squared, right? That's my initial velocity and my mass and so on. And this is the force of friction. And so this is 1/2 times 65 kilograms times 6 meters per second squared over 450 newtons. .6 meters. And so it's just the work done is the change in kinetic energy in this problem. So a useful energy consideration is called efficiency, and it's basically the useful work output over the energy input, or the work out over the energy in. And so some examples of these is and here's the activity. So these are a few of from your book. Cycling is about a 20% efficiency, which means that, you know, if you're on a bicycle, of the calories you burn, 20% of them are actually cranking the pedals, right? The rest of them are producing heat and other activity inside your body that doesn't move the bike forward, right? Swimming is about 2%. Weightlifting T there. Weightlifting is about 9%. And so I'll just put the efficiency here. So here's a gas engine. Gas engines are about 30% efficient, which means 30% of the energy in your gallon of gasoline goes into actually turning the engine over. A huge amount of it gets converted into heat and other things. Right, a diesel is a little more efficient. It's about 35%. By the way, these are pretty close to maximum allowable by the laws of thermodynamics. It turns out you can't get 100% efficiency. And so when, hopefully you'll cover that in maybe your chemistry class. We don't cover it in this physics class, but electric motor. It's like 98% efficient. This is why you can kind of use electric cars. Turns out that converting gas power or coal power or something into electricity is about 30% efficient, but then running that electricity is very highly efficient. So it doesn't cost that much more to have a gas motor, to have an electric motor instead of a gas motor. Also, you can of course charge an electric motor off of renewables or something like that if you want to. Solar cell. These are about 10%. So if you put a solar cell out in your yard or put solar panels on your roof, the maximum energy you can get per maximum power you can get per square meter is like 1,300 watts. That's what the sun delivers to a square meter, so you can't get more than that. But of that 1,300 watts, you're only getting about 130 watts of electricity. And so there's all kinds of inefficiencies that go on in these solar cells. And engineers are trying very hard to make these more and more efficient so that we can get more and more good, useful energy out of the solar cells that we use. And of course make them more reliable and more robust so they don't get destroyed in rain or hail or something like that. All right, that's a little bit about efficiency.